Unseen podcast.
In 2020, a single fraud scandal uncovered nearly $3 billion in fake collateral. Counterfeit gold has deeply infiltrated the global financial system. Modern forgeries are engineered masterpieces. They are meticulously designed to slip past veteran dealers and even official certified mints. The secret to this deception relies on a heavy industrial metal, tungsten. Counterfeiters take raw rods or spheres of tungsten and wrap them inside a relatively thin shell of real gold. This is a highly effective trap because tungsten and gold share almost the exact same density. If you put a pure gold bar and a tungsten-filled fake on a scale, the mass readings will be identical. Traditional weight tests fail completely. Because these adulterated bars look and weigh exactly like the real thing, the entire global market is left wide open to invisible, high-stakes deception. If weight won't give away the forgery, the only guaranteed way to expose that hidden tungsten core is to physically cut the bar open or drill deep into it. But that creates a massive legal problem. Under laws like Malaysia's Pawnbroker Act of 1972, collateral must be preserved in its exact original condition until a transaction is finished. Even beyond the law, drilling a hole into a 10-ounce bar immediately ruins a huge chunk of its resale value, a disastrous outcome if the gold actually turns out to be real. Standard non-destructive tests aren't much help either. X-ray fluorescence and ultrasonic scanners usually only read the surface layer and simply cannot penetrate deep enough to spot the tungsten buried inside. The precious metals industry urgently needs a way to peer deep inside these bars without leaving a single scratch on them, or else risk a complete collapse of trust. Researchers are developing a non-destructive method called photoacoustic sensing. It uses a pulsing laser beam to essentially listen to the internal structure of an object. The process starts by firing fast laser pulses at the target. The surface of the bar absorbs the energy and heats up locally. This rapid spike in temperature causes the metal to physically expand and then quickly contract at a microscopic level. Those tiny rapid movements create high-frequency ultrasonic waves that ripple through the inside of the metal, much like dropping a stone into a still pond. Because gold and tungsten have distinct thermal properties, they respond to laser heat differently. They effectively sing two entirely different acoustic songs. To test exactly how these materials would sound, scientists used software called COMSOL Multiphysics to build virtual gold bars embedded with hidden tungsten spheres. When irradiated, the tungsten core generated an extreme stress response, reaching a peak stress 10 times higher than pure gold. Interestingly, the highest pressure points occurred right along the edges where the fake core collided with the surrounding gold matrix. These localized boundary hotspots light up the simulation. They act like a glowing beacon for acoustic sensors, clearly marking the presence of a foreign object buried under the surface. If a counterfeiter tries to hide multiple smaller tungsten fragments instead of one large chunk, it creates a wide, chaotic stress field that makes the forgery even more obvious. A counterfeiter might perfectly match the weight of a gold bar, but they cannot hide from the distinct acoustic signature of the metal. This is a dot plot showing how pure gold reacts to different near-infrared laser wavelengths. The stress response is remarkably consistent at 850, 960, and 1310 nanometers, meaning labs can use cheaper, widely available 850 nanometer lasers to get highly reliable results. This simulation paves the way for a compact, non-destructive tabletop scanner. A pawn shop owner or a bank teller could place a bar inside, fire the laser, and instantly map the inside without ever lifting a drill. Securing the authenticity of precious metals protects the wider global economy from massive fraud, directly supporting responsible trade and ethical business practices. To learn more about the physics behind this photoacoustic simulation, check out the full study. For more information, please read the full manuscript on the MJOSHT website. This video was generated with the assistance of Notebook LM.